a fellow faculty member at Vector. Um, I guess in the grand scheme of things, Geoff is a relatively newish recruit to Vector, and I am very happy to be involved in Vector's administration when he was hired. So I learned more about him during his onboarding to Vector, and had a good lunch with him when he started, and visited the institute. He's actually out in UBC, as you probably read. And I did know about Geoff's work before he came to Vector, so he might hate this, like, because when you have a really popular paper, everybody sort of knows you for that paper. But he does have this really influential paper that he was the co-first author on that exposed overconfidence in deep neural nets, and myself and many people in the community read that paper and were influenced by it. And he's continued to work in uncertainty quantification and robustness. And what I said to my engineering colleagues in sending out this talk was that most people know ensembles via like competition winning strategy in machine learning, and sort of little performance enhancer to get you that extra few percent. But I think Geoff's going to uncover for us some subtleties about ensembles and some interesting properties that go beyond their use in winning, Kaggle competitions. So the final thing I'll highlight, it is in his official bio. Geoff's been a leader and major contributor to a number of open source libraries, including GPyTorch, which is pretty heavily used Gaussian process library. So yeah, amazing academic work and contributions to the community. We're very happy to welcome you, Geoff.
All right, thanks so much, Grant, for the nice introduction, and thanks so much for having me. I am really excited to, well, first share my slides, and just to make sure my slides are visible. Yeah, okay, great. Yeah, so I'm here today to talk a little bit about ensembles, ensembles of neural networks in particular. And in their use for uncertainty quantification and robustness, where they've been seeing a lot of use. And I think one of the take-home messages that I have for this talk is to some degree to, I think, really be critical and skeptical, I think, about some of intuitions we might have for nice properties that we hope to expect from something like ensembles, or from any types of methods that we are using, particularly in sensitive applications. Because even though our intuitions might lead us one place, and some sort of first level or high level tests might might show us that there is some promising behavior, it is very much possible that there are some subtleties under the hood that actually could be causing potentially detrimental effects. So just very briefly, I guess, a central theme that I have in my research generally is, how do we make reliable decisions assisted by machine learning models? In particular, making these decisions with uncertainty, though also recognizing that the uncertainty that we would often be getting when we're using machine learning models is at best going to be some heuristic notion of uncertainty. I know a lot of people are very interested in, using machine learning models, and thinking about making decisions with machine learning models. I really want to highlight the role of uncertainty when it comes to making decisions with these machine learning models. And so why uncertainty is really important when we, want to make decisions. We can turn to often what I consider, the usual suspects when someone gives a talk arguing why uncertainty quantification is really important. We can always turn to things like safety critical applications, self-driving cars, or things like that, where if we don't recognize a pedestrian, this could cause loss of life, and so we really want to make sure that we're not trusting any decision that we shouldn't be trusting. We want to make sure that a machine learning model knows how much it doesn't know. I think uncertainty quantification, often comes up in kind of like classic scientific inference questions, where maybe we're trying to figure out some a new dust cloud in the Milky Way, and we're doing this through some through some telescopic observations, and we want to be able to put some sort of confidence interval or credible interval around whatever quantities we have. So because we want to really express sort of like how much scientific certainty do we have in these findings. And so we can look to a lot of, sort of these kind of classical arguments for, why uncertainty matters. And these are very much important. I think, though, oftentimes making sure that we have good uncertainty kind of goes beyond just these usual suspects and really influences, I think, any matter of decision-making processes that we might have when it comes to using machine learning models. So something I work a lot on is sort of like optimal experimental design or Bayesian optimization, where oftentimes what we want to do is we want to be using a machine learning model or some other sort of statistical process to basically take in observations that we already have through running prior experiments and help us plan what is going to be the next best experiment that is going to give us the most possible information or work towards a particular goal we might have. One application area where this comes up a lot now, which is really popular, is thinking about drug design with assisted by machine learning. And typically we end up having this classic like experimental design loop where we will have, some set of data that we have. So we'll have, some chemicals and perhaps their known efficacy, for some particular disease or, some reasonable proxy of their efficacy. And we will train a machine learning model based off of these, known quantities that we have. But then we will also use this machine learning model to try to plan the next experiment. We'll run this next experiment, test out this new drug, figure out its efficacy or through, some proxy. This can be added to our data set, and we get this nice sort of like feedback loop where as we're running more experiments, we're gaining more data, which is improving our machine learning model. Uncertainty is super, super crucial in thinking about the decisions that we're making and thinking about the experiments that we want to run next. And the reason that uncertainty is really important is because it's going to help us balance out this like exploration versus exploitation trade-off, right? We need to know what regions of this large input space that we're working in have we not previously explored, where we don't necessarily have enough information to say like we know exactly what the effects of these types of chemicals are going to be. And having that uncertainty information gives us a very principled way to balance off this exploration versus exploitation when it comes to designing experiments. So thinking about here's some set of potential drugs that might be very useful versus like here's some chemicals that we haven't explored. There could potentially be some use we just don't know. And what I found in a lot of my own research and what you'll find throughout the literature is this uncertainty is super, super crucial for that and really helps to enhance the performance of experimental design. Another area, and this is something I haven't worked in very recently, but something I worked on early in my PhD, thinking about the role of uncertainty when it comes to algorithmic fairness. And this is, I think, something that often can get overlooked. So, if I potentially have some sort of classifier that, is being used to make a decision, something that could be, for example, trying to determine, whether or not like assist in hiring or assist in, trying to give out loans to people. Of course, there's been so much discussion about how any sort of algorithm that is being used in a decision-making problem like this could have disparate impacts. It could amplify biases that already exist in the data or introduce new biases. And so there's been a lot of work in algorithmic fairness, thinking about how do we mitigate those biases? How do we ensure that we have equal outcomes or equal opportunities for different groups? And what I uncovered in some of my research early on in my PhD is the role that uncertainty plays there. And in fact, having a good notion of uncertainty and paying attention to that notion of uncertainty can have dramatic impacts on the potential outcomes that you would get from these models. And if you have a very bad notion of uncertainty, this can be exploited essentially by a decision maker to eventually lead to worse outcomes. So thinking about the role of uncertainty in any sort of decision-making application, it really goes beyond just, like self-driving cars and personalized medicine. It really impacts any decision-making process that is involving a predictive model that we have from machine learning. And so today, that was sort of like a high-level overview of, various kind of applications where I have used, or thought about uncertainty for decision-making. Today, I'm not going to really focus on a particular application, but what I really want to focus on is where we're getting these uncertainty estimates from and how good are these uncertainty estimates, and can these uncertainty estimates themselves be useful for decision making? And this is, figuring out how we get good uncertainty estimates from machine learning models. This is a very challenging problem that a lot of people have thought about. a lot of people have worked on, and it becomes a lot harder as our models become more and more complicated. It's fairly straightforward if we have a very, very simple models. If we're working with like linear regression or even some decision tree models, it's not too challenging to get a reasonable notion of uncertainty from them. When we're dealing with very, very large neural networks, this is something where now actually quantifying uncertainty in a meaningful way is very challenging. One method that has seen a lot of use in the literature is ensembling multiple neural networks and basically using multiple neural networks to gain a heuristic notion of uncertainty. This has been something that has been adopted as a gold standard and has a lot of potential benefits and a lot of potential use. But what I want to talk today about is a bit of a negative result that we found when we really started looking under the hood of neural network ensembles and really questioning how useful are they, especially for decision making when we're thinking about their uncertainty properties. And I guess to kind of cut to the punchline here and kind of talk about the high level points of what I'm going to be discussing is, even though, as I will discuss, there's a lot of really good intuition behind why we should be using ensembles and neural networks and why they would, in theory, provide really good notions of uncertainty that we could use. The notion of uncertainty that we often get from ensembles is not actually beneficial for decision making. And I'll show a few examples of where this arises. This, though, isn't just like some sort of empirical finding where it's saying, okay, this current generation of neural networks that we have is potentially has some sort of problem with it that we can overcome through slightly different training methodology. The fact that ensembles are not don't provide a meaningful notion of uncertainty that can be used for decision making really appears to be this consequence of overparameterization, of using these very, very large neural networks. It's this more fundamental problem that isn't necessarily due to any sort of specific architecture, but simply through the use of very, very large models, where these models are much, much larger than the amount of data that we have. And what we are seeing is that sort of the degradation of the ability of ensembles to provide these meaningful notions of uncertainty that can be useful for decision making is becoming worse as models become increasingly larger. So this is, I gave a version of this talk where I said this was troubling trajectories for uncertainty quantification. And the reason I say that is because the trends that are going into neural network development, and as we're making models larger and larger and larger, are, at least when we're using sort of ensembles as I'm going to be describing them in this work, are going to further hamper the ability of getting good uncertainty estimates out of neural networks, at least with this one method that has been so popularized throughout the machine learning literature. All right, so I want to dive first into thinking about neural network ensembles for uncertainty quantification and judging their abilities on some decision-making tasks. And I guess before I dive into this, I also want to say, I'm happy to answer questions along the way as they come up. So, please feel free to interrupt with any questions. So, before diving into ensembles in particular, what I first want to mention is, when I'm saying we want to use uncertainty for decision making, what do we really want, and how is uncertainty going to be useful for decision making? It really comes down to not just having some sort of notion of uncertainty, but a notion of uncertainty that we can decompose into different components that tell us about the source of that uncertainty. So two terms that get thrown around a lot in the literature, and I'll try to constantly remind you of these definitions because the wording is potentially a little dense here, but it's these notions of epistemic and aleatoric uncertainty. The basic idea is thinking about is the notion of uncertainty that we have reducible through collecting more data. So epistemic uncertainty is basically uncertainty that we have in the model itself. And the reason that we have uncertainty in the model is basically just due to the fact that we have limited data. If we had observed more data, if we had observed a slightly different data set, we probably would have gotten a different model through our training procedure. And so I want to be able to capture a notion of this epistemic uncertainty, which is, again, this where I can think about the source of that uncertainty being due to just a limited amount of data, uncertainty that I could reduce by collecting more data. I want to differentiate this epistemic uncertainty from aleatoric uncertainty, which is sort of the opposite. That's an irreducible uncertainty. this would be, say if I have a image classification neural network and I just get a picture that is super, super blurry, there's no way from that super blurry picture that I would actually be able to like identify anything in that picture. That's irreducible uncertainty. From this image, there was no way to tell, whether there's a dog or a cat or a bird in that image. And it's useful to distinguish, and actually very necessary to distinguish between this epistemic versus this aleatoric uncertainty, this reducible versus irreducible uncertainty, because that's going to help me make decisions downstream. For example, if I am able to say, here is, some particular data where I have high uncertainty in my model's predictions, and I know that it is epistemic uncertainty rather than aleatoric uncertainty, this could tell me, potentially this data is coming from, something that my neural network did not see during training. And so I shouldn't trust its prediction for that reason. Maybe I should actually go back and collect more data from here. So this could be useful when I'm thinking about designing experiments, knowing that here is something my model didn't encounter during training. It's probably something that would be useful to explore and collect more data from there. So it's really useful to be able to divide uncertainty into these two categories. And being able to identify epistemic uncertainty and differentiate it from aleatoric uncertainty really, I think, what was this idea that inspired the use of ensembles of neural networks for uncertainty quantification in the first place, where ensembles would give us this ability to actually separate these two sources of uncertainty and be able to distinguish between them. And the intuition is kind of nice. Before I begin with that intuition, though, I want to highlight when I'm talking about ensembles and neural networks, typically what I'm going to be describing throughout this talk, though I'll bend that definition a little bit, is I'm going to have multiple copies basically of the same neural network architecture. They're all going to be trained on the same data set, and they're all going to be trained, independently. They're not going to know that much about each other. The only differences between these neural networks basically amount to how I choose to initialize these models and, how I choose to order the data when I'm training them. But because, neural networks are, these complex beasts where the training is highly non-convex, just having these the slight differences in the randomization in the training procedure will actually lead to different models at the end of the day. So the reason that I think ensembles are going to be really useful for, and the reason that the community has adopted for ensembles being really useful for uncertainty quantification, and particular dividing amongst these reducible and irreducible notions of uncertainty is, if my model is encountering data that is similar to what it saw during training, then it's likely that all of these different models, that have these slight differences between them are going to produce the same prediction. But now, instead, if I fed something just totally unrelated to these models, something that my model, that like totally dissimilar from anything my models encountered during training, now there's nothing constraining these models to produce similar predictions. And all of this inherent randomness that I'm getting through the training procedure, it should actually make these models arise at different predictions. Because again, there's nothing constraining them from the training process to actually produce the same thing. So if I see that all of the models in my ensemble are making different predictions, that is a good sense that I should have high epistemic uncertainty, at least intuitively. It means that this is probably not something that I encountered during training. I would be able to reduce this uncertainty if I collected more training data that was similar to what my model was seeing at this point in time. And there's a lot of papers that have sort of used this intuition to justify the use of ensembles for actually, for quantifying uncertainty in this way. So there was a landmark paper called Simple and Scalable Predictive Uncertainty Estimates from Deep Ensembles that really popularized this idea. And since then, they've been used in a lot of applications, from safety critical machine learning practices to also uses in reinforcement learning, where again, we have this decision-making process where it's useful to separate reducible versus irreducible uncertainty. And I think there's a lot of good reason to at least at first trust that we are getting good uncertainty estimates from ensembles, where here what I'm showing is a common plot that you will see when we're trying to think about how good the notion of uncertainty that we're getting is. It's known as a reliability diagram. What I'm plotting is I'm on the X and Y axes are basically the confidence estimates that I would be getting from a neural network, and basically conditioned on that confidence estimate, how accurate is my neural network when it is making predictions with that level of confidence. And ideally, what I would like to be seeing is if I have a well-calibrated notion of uncertainty, then my confidence should be matching my accuracy, at least at that confidence level. For example, like if I had a, if I was trying to predict the weather and I say that there's a 60% chance that it's going to rain, well, for all of those predictions that I'm, making, where there's a 60% chance of raining, it should actually rain 60% of those times, where that confidence notion is actually reflective of the ground truth likelihood of rain. And so that's kind of what this reliability diagram is capturing. Here we see that ensembles are actually providing a fairly well-calibrated notion of uncertainty where the confidence does match the accuracy. And that should be a good sign that ensembles are providing a reasonable notion of uncertainty. But a crucial point I want to make throughout this talk is calibration isn't decision-making, right? Calibration just basically says the notions of confidence that I'm providing are probabilistically meaningful, like they match ground truth likelihood of correctness. But it doesn't necessarily mean that these uncertainty estimates that I have will actually inform better decision-making, especially in applications where I really need to be able to separate the known unknowns versus the unknown unknowns, what could be reduced from collecting more data versus what is just inherent noise that's present in the data. And so let's actually now evaluate using ensembles for a particular decision-making application. So a very basic one that you'll see often throughout the literature is what's often called OOD detection, where OOD stands for out of distribution, or often known as anomaly detection. So the idea here would be if, for example, I have all of these images of clothes, if there was just something that did not make sense in that particular data set, like for example, if I have a neural network that's trained to look at pictures of various fashion items, and then all of a sudden here is just some number that appears. This is clearly not an item of clothing. I would want to be able to recognize that and be able to detect that anomalous data that comes into my neural network. Here is a prime example of where we should, if we have a good separation between our epistemic and aleatoric uncertainty, again, this reducible versus irreducible notion of uncertainty, we should really be able to use that to our advantage. As I look at this 3 that I see here, right, like it's not a blurry image, right? Like I should be able to tell what is in that image, but my model hasn't encountered anything like that over the course of training. So this is reducible uncertainty. If I had seen more of these particular images, my model should be able to say what is in that image with high confidence. And therefore, being able to separate the epistemic versus aleatoric uncertainty, if I have an image that is high uncertainty, but it's really this epistemic, this reducible notion of uncertainty, that gives me reason to expect that this is anomalous for the particular data that I train my neural network on. So again, we want to think about ensembles providing this nice notion of epistemic uncertainty. And in particular, it's going to be the variance amongst these different ensemble members. So if the ensemble members are all making different predictions, that should be indicative of high epistemic uncertainty. And what we find is that this is in fact true in practice. What I'm showing here is basically the measure of uncertainty, where this is of course, sorry, I believe actually there's a typo there on the x-axis. This should be not single model uncertainty, but the amount of variance amongst the different ensemble members that I have. And what I'm plotting on the blue line is data that is in distribution, data that is very similar to what I encountered during training. And on the orange line, I'm plotting the amount of the density of uncertainty estimates that I would get from out of distribution data, anomalous data. And what I see here is I have it is more likely that when I'm using anomalous data, that I would receive more variance amongst the different members in my ensemble, which is in theory a good thing. This is kind of what I wanted. This is feeding into the intuitions that I had about ensembles, that I should be seeing much more variance amongst the different predictions of the members when there's something that is very dissimilar to what I encountered during training. However, what we then found is that this higher variance is, if we start controlling for more factors in the particular neural networks, what we found is that this notion of variance that seems to be higher for this anomalous data actually goes away. Remember, we really care about separating these two notions of uncertainty, the reducible versus the irreducible.
And when we then condition on this signal that we think should be capturing the irreducible uncertainty from the ensembles, and we now are trying to differentiate condition on various levels of this irreducible uncertainty, is there a meaningful difference now between these epistemic uncertainty estimate for this anomalous data versus this in-distribution data? What we find is that that difference actually goes away. And so again, epistemic uncertainty is this reducible, aleatoric is this irreducible notion of uncertainty. And so what we find is that even though ensembles are expressing more variance for these anomalous data, which is again something that we would like to see, we would like to see that we're able to have more uncertainty for data that is likely anomalous. What we find is that that is basically almost entirely due to just having higher levels of uncertainty in general. It's not due to having this nice, clean separation of reducible versus irreducible uncertainty. And that's going to be very challenging now for this particular task, because we aren't necessarily able to distinguish what is truly an anomalous data point, something that is a nice clean image, but not necessarily something that is representative of the training data set, from data that is just noisy and hard to classify in general. And so that was an example of where ensembles are actually not necessarily going to be too useful for this one simple decision-making task of detecting anomalies. Throughout the literature, in recent literature, there's been a number of other examples of where, when we're trying to use ensembles for these decision-making applications, where we really care about separating these two different notions of uncertainty, what we find is that they often underperform what we would expect. Here again is examples of using ensembles in Bayesian optimization. This isn't work that I've done. This is work done by some of my collaborators, where Bayesian optimization is one way of doing this optimal experimental design that I talked about, where again, we really care about knowing where we haven't necessarily collected a lot of data previously to balance this exploration versus exploitation trade-off. And what we find is that even though ensembles in theory and throughout the literature have often provided these really well calibrated notions of uncertainty, often a lot more calibrated than other methods, when we actually now use these uncertainty estimates to try to make decisions, they often underperform many other methods. As you can see by the black line here on these plots, often being outperformed by other methods, in part because these notion of reducible and irreducible uncertainty are so intertwined and hard to pull apart. So what I've shown is that, or at least given a glimpse of, is that even though we are getting something that looks good on paper when it comes to the uncertainty estimates that we're getting from ensembles, when we actually try to use it to inform better downstream decisions, we're often falling short because we can't separate out, again, the known unknowns versus the unknown unknowns, the reducible versus the irreducible uncertainty. And I think that there is lots of things that we could point to in ways that we could be improving how we're thinking about combining multiple neural networks, especially if our goal is to try to get notions of where we have reducible uncertainty. There are many different variations we could make to the basic ensembling framework to try to improve how the uncertainty estimates that we get. But what I hope to now convey in this next part of the talk is that even though there are going to be some places where we can make slight modifications to this formula, a lot of these efforts might actually be in vain, because a lot of what we're seeing from the uncertainty estimates that we're getting from ensembles is going to be this fundamental consequence of the fact that we're using very, very large models. So what I'm going to present comes from some recent theoretical work, and I want to just quickly highlight some of the key ideas for the theory that we developed. So we wanted to try to analyze, why are we getting uncertainty estimates that might not necessarily be useful for decision making from ensembles? And we wanted to analyze this from a theoretical perspective to see if there's any sort of fundamental property of, say, high dimensional statistics that is actually contributing to what we're seeing. And so what we turned to is looking at a model known as a random feature model, which is often used as an approximation for neural networks when people want to try to theoretically analyze neural networks. What a random feature model is it's basically a one hidden layer neural network, where rather than training all of the weights in the neural network, we are only training the very final set of weights, the solid black lines on this plot, and all of the weights that exist in the hidden layer, those are going to be fixed at a random initialization. So this is, very similar to what a neural network is, except for we're only training some portion of the parameters, not all of the parameters. But what's very useful about this particular approximation is now the model is linear with respect to the learnable parameters that we have. The only parameters that we're learning are these final output weights theta. The prediction that we're going to be making is going to be, taking what we had in the hidden layer and multiplying it by theta. So this model is now linear with respect to its learnable parameters. That makes it very easy to analyze from a theoretical perspective. So we are going to then think about ensembles of these random feature models, and sort of mirroring what we see in practice with the way that people are using ensembles of neural networks for uncertainty quantification tasks, is we're going to make many copies of this random feature model that are all going to differ basically on how we initialize them. So each of these models is going to have a different set of random hidden layer weights that again stay fixed throughout the course of training. And so this is going to cause them all to make different predictions. And as we would do when we're making predictions with neural network ensembles, we would consider doing, say, like a simple average of the different predictions that we would get out of these models. And, of course, we could then think about the variance amongst the different predictions we're getting from these m different models in our ensemble as a notion of uncertainty that we have. So the variance amongst all of these models, this is going to sort of be given by, what is the average difference between any one particular model and the ensemble average. And importantly, the ensemble average is going to be very similar to what we would get from the expected model, right? Like, if we thought about like thinking of every possible random feature model that we could have trained on our particular data set, like that is ultimately what the ensemble would converge to if we had infinitely many ensemble members. Right. So as we're thinking about ensemble variance, again, as this notion of uncertainty that we want to be using for decision-making tasks, for those of you who have seen sort of like the double descent literature or this idea of double descent that has emerged recently, another place that we often like to think about variance amongst models when we're like analyzing different machine learning models comes from the bias-variance decomposition of risk. And so, this very classic result in machine learning that basically takes some sort of notion of predictive error that we would have and decomposes it into two terms, one of which is what we consider the squared bias, which would be the error that we would have from the expected model, where the expected model is where we're averaging out all sources of randomness from the model. And I'm sorry, there's a typo there. That should be a plus sign, not a minus sign. But it decomposes into the squared bias, and then also the variance amongst the different models that we have. So this variance term that we're analyzing from ensembles is also something that we have often analyzed when we're trying to think about the risk of a particular machine learning model. And in the last 5 or 6 years, we've had this kind of radical shift in our understanding of this bias variance decomposition through a phenomenon that Mikhail Belkin coined as the double descent phenomenon, which is typically we thought of as models become more and more complicated, their bias goes down. The expected model becomes a lot more accurate, a lot closer to what the true data would be. But the variance increases. We end up with this, because there are many possible models that could fit the data, we're not able to necessarily nail down the expected model through a finite amount of data. And so we see the variance increase. This is sort of the classical notion that we had about the bias variance trade-off, but in recent years, what we have seen is that actually, when we make our models really, really large, we see this weird phenomenon now where both bias and variance are decreasing as we continue to make our model more and more complicated. And this is where we think that neural networks live, is in this overparameterized regime, where they have the capability of learning any training data set absolutely perfectly. And so they live in this regime where we don't really totally understand the bias variance trade-off from sort of a classical perspective, where we're seeing variance actually decreasing as we're making our models more and more complicated. And why I bring up this double descent curve right now is thinking again about what we care about which is the variance of ensembles when we're thinking about making predictions, variance has come up recently in thinking about how neural networks behave really differently than classical models from this bias variance perspective of risk. And so what we would expect is that if neural networks are living in this overparameterized regime, which behaves fundamentally differently from a bias variance perspective, there might be something weird that's happening with ensemble uncertainty estimation in this regime as well. And so what my colleagues and I developed in a paper that's currently under submission is we analyzed again this random feature model and the risk of this random feature model and thinking again about the difference between this sort of underparameterized regime, this classical regime where we really understand that bias variance decomposition very well, versus this new overparameterized regime where we have these really, really powerful models like neural networks, where for some reason making them more and more powerful seems to actually be better both from a bias and variance perspective. And what we found is that when we analyzed the bias term in particular, we found that something very interesting happened, which is that the bias term, when we thought about these random feature models in this overparameterized regime, basically ended up being a constant. In particular, what we found is that the expected random feature model was exactly equivalent to a random feature model that was infinitely large. And this was not true in a more classical regime of machine learning. So as sort of an informal summary of what we found is if we thought about the kernel ridge regressor, so basically a model that would kernel ridgeless regressor that would correspond to basically this random feature model as we made it infinitely wide, what we found is that an ensemble of infinitely many models, that average of that ensemble would eventually exactly correspond to this infinitely wide model as we made the ensemble larger and larger and larger. And here we verified that through some experiments. What I'm showing here is I'm comparing on the left, this is an ensemble of multiple of random feature models trained on this very simple data set. Each of the blue lines represents the predictions from any given ensemble member. And then the dotted line both represents what I would have gotten from a single infinitely wide model, but also what I get from the ensemble average. I'm showing on the right, again, just a simplified version of that plot, which has the, again, infinitely wide model and the ensemble average. We see them perfectly correspond with one another. This is also something that we saw then when we replicated this experiment with actual neural networks, where we were comparing, say, an ensemble of large but not too large neural networks versus one single very, very large neural network. And what we saw in practice was that there was a lot of correspondence on a pointwise basis between these models. So actually, the types of predictions that we were getting from one single very, very large neural network actually corresponded really well to the predictions that we would get from an ensemble of not so large neural networks. And this was true both on in distribution and out of distribution data. So data that was similar to what the model saw during training and data that was very different. So what does all of this have to do then with uncertainty quantification? And why do I think that this actually helps explain a little bit about why we were seeing uncertainty quantification from ensembles not being super useful for the purposes of decision making? Well, going back to what we talked about when we thought about ensemble variance, we described that ensemble variance is, I could think about that as the difference between any individual model in my ensemble versus the ensemble average. So basically, another way I could think about it is I could think also about what is the difference between the error I would expect from any one single model in my ensemble versus what is the error I would expect from the ensemble average. If I thought about the mean prediction that I'm getting out of this ensemble, that is what ensemble variance seems to be capturing. But also what we uncovered from this recent theoretical work and from some of the experiments that we did with neural networks is that the ensemble average seems to correspond really well with one single very, very large neural network, right? There is not much difference between using it on, at least as far as the average prediction goes, there's not much of a difference between using an ensemble of many neural networks versus using one single very, very large neural network. And so putting these two pieces together a new way that I can frame the uncertainty that I'm getting out of ensembles is the variance I'm getting from ensembles exactly captures the expected effects I would get if I took my model and I made it a lot larger. When I'm seeing variance amongst ensemble predictions, this is really what I'm measuring here. It's not necessarily measuring some very traditional notion of uncertainty. Instead, it's basically saying, what would happen to the predictions I'm making from my ensemble? Or sorry, what would happen if I have a single model? What would happen to its predictions if I were to have taken that model and just made it a lot bigger? It's the expected effects of increasing capacity. And I'm not necessarily arguing that this is something that we shouldn't care about, something that doesn't necessarily have any use. What I am arguing, though, is there's no real basis for expecting that this is going to work well in a decision-making application. Typically, when we think about uncertainty influencing decision-making, we often think about having, a very classical frequentist or Bayesian notion of uncertainty. And this thing that we're getting out of ensemble variance, basically the expected effects of increasing capacity, there's no real basis for understanding why this would actually be useful for decision making. And just to show that there is a clear difference between this effect and sort of more classical notions of uncertainty, what I'm showing on the bottom here is basically the ensemble variance on the left for a bunch of different points coming from an ensemble that was trained on this particular data set. Versus sort of a more classical notion of uncertainty that I would expect. This would be a Bayesian notion of uncertainty. And they correspond in certain places, but they can be quite different in other places. And so this is really going to have an effect then if I'm trying to use this notion of uncertainty for decision-making applications. All right, moving on to the final part, and this should be this part should be relatively quick, and then we can move on to taking questions. So what we saw in the first part is that there are some limitations to using ensemble variance and getting meaningful improvements on decision-making tasks. In that last part, I claimed that part of the reason is actually sort of this fundamental property that what ensemble variance is capturing is it's capturing this very weird notion of uncertainty. And it's capturing this very weird notion of uncertainty in particular because we happen to be in this new regime that isn't super well analyzed or is only starting to become well analyzed, this overparameterized regime where weird things happen with the variance of different models. And so now in the last portion of the talk, I want to talk a little bit about sort of the trajectory that I see here and thinking about is there any chance that we will be getting a more meaningful notion of uncertainty out of neural network ensembles if we were to try to make certain modifications to the particular neural networks that we have. So again, this is the this is sort of again our standard recipe that we have for neural network ensembles, where we're taking basically again the same architecture, the same data, doing this independent training of these models, and we're just sort of relying on these different sources of randomness in the initialization and in the training procedure to produce different models. This was also again sort of the basis of the theoretical model that we analyzed in the last part of the talk. And it seems that if we want to get a more reasonable notion of uncertainty, especially one that adheres to this uncertainty decomposition that we care about, separating the known unknowns from the unknown unknowns, the reducible uncertainty from the irreducible uncertainty, it seems like this recipe isn't actually the recipe that we would want to use. There's a lot of things that are being held constant here, like the same architecture and the same data. Maybe we would be better able to capture this notion of epistemic uncertainty, this reducible uncertainty, if we introduced more notions of diversity into the different component models that we're using here. What if we perhaps use different architectures rather than relying on the same architecture, or use different training procedures? And this would potentially give us a notion of how much the particular predictions that we're getting are specific to a particular model architecture or a specific training procedure. Again, sort of capturing how much is really dependent on the particular, the particulars of the model, how much is particular to the fact that we have a limited training data set. So it seems like there's a lot of opportunity for improvement here if we just stop making everything exactly the same and just relying on these few sources of randomness. I think to illustrate this concept in a little bit more detail, so thinking again about this like decomposition between bias and variance, another way I could think about ensembles in particular is because ensembles are ultimately I'm averaging away out different sources of randomness, and I'm moving more towards some notion of expected model. I could then think about the error that I have from an ensemble decomposing really nicely into two terms. So the error I have from a given ensemble is both due to, I could think about it as being due to what is the average error I would expect from any one single model in my ensemble if I was using it independently, not using it as part of an ensemble. And then I'm going to be subtracting off the variance amongst all of these different models. So this is like, if I just rearrange this equation, I would get something that looks very, very similar to the bias variance decomposition that we saw in the previous set of slides. And the m minus 1 over m normalizing term, that's basically to account for the fact that we have only a finite number of members in our ensemble. And so this is really nice because then I can, if I want to think about an ensemble and I want to reason about it, I can plot it on this plot that I have over here on the top, which is again using this decomposition I have below to visualize the ensemble error that I have. So on the bottom, I'm showing the amount of variance I'm getting from my ensemble predictions. The y-axis is showing now the average error I'm getting from any one single model in my ensemble. And then the diagonal lines, basically due to this decomposition I have below, is then plotting the level sets, or is plotting level sets, sorry, of error I would expect from my ensemble. So I'm really seeing these sort of two avenues I would have to making an ensemble better, or the ensemble average better, just from a simple error perspective. I could choose to either, keeping all of the models that I have in my ensemble, they could all have that same expected risk. And I could just simply think about how do I make these models more diverse, have more variance amongst them, where then ultimately, that variance gets, averaged out through the ensembling process, which would make my average prediction better. Or alternatively, what I could do is I could, keeping the amount of predictive diversity I have amongst these models constant, I could think about just using better models. And that would also be a way to reduce the error that I would have in my ensemble. So if I took all of these different models that I have, which again are like the same architecture, same training procedure, all of that, and I increase like diversity amongst them by using slightly different architectures, slightly different training procedures, in theory, what I should be able to do then is I should be able to move across this x-axis. I should be increasing the amount of diversity that I have amongst these different models. And that would be beneficial because, not only then am I capturing more variance, which would hopefully give me, better notion of epistemic uncertainty, but I'm also getting a better ensemble in the result because I'm moving across these level sets of ensemble error. And so we ran an experiment and we found that this was actually true in practice. What we did is we took what we called these homogeneous ensembles, these ensembles of where we take, again, this standard recipe. We have, the same neural network architecture copied many times, just differing in terms of the randomness that arise in the training procedure, and replacing that with what we call the heterogeneous ensemble, where we, now basically we relied on, the same data set and many similar training procedures, but we were using many different model architectures, to hopefully get a little bit more, diversity in the different models that we had, because the different model architectures would presumably, perform in slightly different ways. And what we found is that this indeed helped us move across these level sets. We were able to use models that all got very similar performance individually, but now because they were different model architectures, they were a little bit more diverse, which gave us a little bit extra variance, that was useful for uncertainty, or for uncertainty, for decision-making applications, and helped us, ultimately end up with a better ensemble. We found, though, that there was an opportunity cost to doing this, though, because ultimately, at the end of the day, if I want to have a really good ensemble, one that's able to, make really, really good predictions on data, which is also something I care about. I don't just care about, having good uncertainty. I also care about making good predictions. This was not the optimal recipe towards improving the ensemble that I had. The optimal recipe was, rather than replacing each of these individual models with like slightly more diverse components, instead, if I just made all of the models in the ensemble a lot larger, made them more powerful, this really, really reduced the ensemble error that I saw, but it also really came at the cost of increasing the diversity amongst the models for reasons that we saw with the double descent curve earlier, that as we make our models larger, we're actually reducing the amount of variance amongst them. And we found this to be a little bit troubling, because this is really a sign that it's going to be really hard to capture, increasing amounts of uncertainty as neural networks become larger and larger and more powerful. This is, if we want to think about making better predictions, which ultimately will in and of itself lead to making better decisions, we will be using models that become more and more and more similar. And in doing so, it's good because that's what happens as, at least empirically, as we're making models larger and larger, they're becoming more similar. And this means that we're going to be capturing less and less predictive diversity that could be useful for decision-making applications. So showing this actually now on real data, what I'm showing here are ensembles that we train on the CFAR10 and ImageNet image classification data sets. Again, I'm showing this error decomposition that we talked about earlier, considering both the part of the single model error term on the y-axis and the amount of predictive diversity that we have, where the diagonal lines correspond to level sets of ensemble performance. And what we found is then the ensembles that performed the best, so these are going to be, again, the ensembles that are lowest on the level sets of this curve, are generally going to be the ensembles that are on the lower left-hand corners of this graph. So these are going to be models where we have these really powerful individual models that compose this ensemble, but ultimately models that aren't really that diverse, aren't making that very different predictions. And of course, this would be fine if we were able to, make if each of the model in our ensemble was able to make predictions with 100% accuracy. That would be great. We wouldn't need any uncertainty in that case. But what we can see from these graphs is that's clearly not the case. Even as our ensembles are basically becoming, or the members of our ensemble are becoming so similar, they're basically almost identical, they are still making errors. We are not achieving 100% perfect accuracy. And this is troubling because by trying to make these models more powerful, we are basically removing this signal that we would have that potentially could be useful for uncertainty quantification, and almost removing it entirely, but not necessarily removing the need for that uncertainty, because we are still making errors and we want to be able to quantify those errors. Very quickly, because I realize we're coming up on time here. What we found was that also, this was just sort of looking at one way of trying to increase diversity, through amongst the ensemble members by using different model architectures throughout this paper that was published in TMLR and also at ICLR last year. We saw that other notions of trying to increase predictive diversity amongst these models to try to get better variance estimates, they often were very detrimental as well. And these techniques that were very good, sort of in the more classical ensembles of thinking about techniques like bagging, boosting, things that had worked really well for like ensembles of trees earlier on, tend to actually backfire in the case of neural networks, where they ultimately lead to worse ensembles that are going to be worse overall for decision-making applications. So to just summarize the takeaways that I brought up in the beginning of the talk, neural network ensembles, there's many reasons to use them. Like I don't mean the takeaway here to be, ensembles are evil and we should never consider using them at all. There's many reasons where there actually can be a lot more practical, even the sort of basic recipe, than using a single larger model. At the same time, what we have found is that we shouldn't necessarily trust that variance amongst many neural networks is actually going to be a useful signal of uncertainty that can help decision making. And this is not necessarily just a problem with our current generation of neural networks, that we could solve by using a slightly different optimizer or slightly different architecture. This really seems to be a fundamental problem of overparameterization and using larger models. And so I expect that neural networks, as they continue to get larger and more powerful, trying to look at notions of variance amongst these different models is going to become even worse as these models increase in capacity. But to not leave on such a low note, here's what I call my glimmers of hope slide. We're thinking about what could we actually do if we wanted to try to get better notions of uncertainty out of neural networks, and especially thinking about, again, this idea of ensembling is so commonplace throughout machine learning. It'd be really great, ensembles have been beneficial for uncertainty quantification, with more classical, smaller models. So here's where I think that there are potential directions for getting more meaningful notions of uncertainty from neural networks, with or without using ensembles. One thing that I think is becoming a very popular topic is thinking about mixture of expert models. So there's lots of recent evidence that a lot of these large language models that are being used in practice, especially things like DeepSeek, are actually these mixture of expert models where we have multiple models that are all working on a very specialized subset of data, that's not something that's really covered by this framework that I analyzed. I assume that all of the models were trained on the same data, are all trained to essentially do the same task. And so I think mixture of experts there, I really am hoping to investigate how mixture of expert models potentially yield better uncertainty quantification. This is mostly focusing again on sort of predictive discriminative models. I think generative models already kind of have this way of getting a distribution of different generations of predictions. So I think there's a lot of potential in using generative models for uncertainty quantification with neural networks. Also having task-aware ensembles, so thinking about if I know that the particular thing I want to do with this ensemble is decision-making, and trying to get useful uncertainty, is there a way that I could modify the way that I either train my models or ensemble them in particular to get better decision-making? So I think that there are definitely avenues to explore here, but I think that in at least the basic recipes that are very commonplace for ensemble neural networks, I think that there may not necessarily, there may be some, or there are some downfalls in trying to use these notions of uncertainty for decision making. And with that, I would love to thank a whole host of collaborators who made this research possible, and I'm happy to take any questions.
Thank you very much, Geoff, for the great talk. I see lots of virtual clapping going on. So I guess we'll move into the Q&A stage. Yeah, maybe I'll kick it off because I had the opportunity to be an external on